So this video is about the limit comparison test. So what we're doing is comparing two series to see if they converge, well, to see if one of them converges or diverge. So suppose that two series are both greater than 0, rather the sequences are both greater than 0, so their terms are positive. The limit comparison says that if the limit as n approaches infinity, so you're looking way out on the tail end of the series, if a sub n over b sub n equals L, where L is both finite and positive, then you can say a sub n, the sum of a sub n and the sum of b sub n either both converge or both diverge. So what we're saying here is that you're checking the relative size because L is a number. If you get infinity, that means that you had a series that was much, much larger, a sequence whose terms were much larger in the numerator than the denominator, so they're not of a size. If you get 0, not something positive, that means that the larger series by a lot was in the denominator. So if you actually get a number that's both finite and positive, these are of a size. So what one does, so will the other. And this is way out on the end of the series, so you're looking out on terms way out towards infinity. So what you do is you look at this just like you would for a direct comparison, and I start all of my comparisons as direct. So for this example, I'm looking at the sum from n equals 1 to infinity of 1 over 3n squared minus 4n plus 5. And I look at that and you want to check convergence or divergence, and that's not a p-series because it has the 3 multiplied, a negative 4n, a plus 5. But you can actually compare it to a p-series because if you look at the dominant term here, the dominant term in the denominator is a 3n squared. The 3 is negligible. We don't really care about that. If you're just looking at a 3n squared, I could actually take this 3, if these other numbers weren't here, and I could pull it outside of my sigma because it's not involved on the other terms because it's the only term there. So if I looked at this series of 1 over 3n squared, it's going to add up to 1/3 the series of 1 over n squared. That's what that 3 does. So we don't really have to pay attention to that. So I look for the highest power of n in my denominator, or if you have n's in the numerator and denominator, you want to reduce them to see what you're going to compare to. So I'm going to compare this to the sum from n equals 1 to infinity of 1 over n squared. And I choose something like this because this is easy to tell the convergence and divergence of. So if you see a polynomial or a polynomial over a polynomial, a rational expression, you should be thinking maybe it's a p-series. And that's where a lot of them, that's what a whole lot of them are because the limit comparison test works so well, so that's what I automatically go to. So I look at this and I'm like, okay, n equals 1 to infinity of 1 over n squared. This is a p-series. And I know that p equals 2. Remember that a p-series is the sequence for the series is a 1 over n to the p. So p equals 2, which is greater than 1. And for a p-series, if your p is greater than 1, we know that this series will converge. If it's less than 1 or equal to 1, it will diverge. So this is a convergent series. So what I want to do is check the relative size, and if I thought this was a direct comparison, I would actually say, okay, if this one converges and this is less than that, then I would be done. So I'd check, I'd say, is 1 over 3n squared minus 4n plus 5, is it less than a 1 over n squared? And for the problems that we did for direct comparison, it's pretty easy to see. We'd have a plus 5 or a minus 6 or something like that. But here we're subtracting 4n and adding 5. You're also multiplying by 3. So you might not be able to tell. Or this could be a false statement and you would say, no, I can't do a direct comparison. So if you aren't sure, and I'm going to declare myself unsure about this, I'm not going to do that, and I'm going to do the limit comparison instead. So to do the limit comparison, I take the limit as n approaches infinity, and I will write the ratio of my two sequences, the a sub n and the b sub n. The order that you write them in, which one is in the numerator, which is in the denominator, doesn't matter. Because imagine that I wrote it as a sub n over b sub n and I got 3. Well, 3 is finite and positive. If I had switched the order, I would have gotten 1/3. Well, 1/3 is also finite and positive, so it doesn't matter which you put in the numerator and which you put in the denominator. So for this one, I'll put 1 over n squared in my numerator and divide that by a 1 over 3n squared minus 4n plus 5. And before I try to take the limit, I'm going to simplify this a little bit. So this will equal the limit as n approaches infinity, and then I'm dividing by a fraction, so I'll multiply by the reciprocal of this. So I have a 1 over n squared. 1 is in my numerator from this, and n squared in my denominator. But when I multiply, this 3n squared minus 4n plus 5 will be in my numerator. So this is what I'm taking the limit of. And if I evaluate as n approaches infinity, I will get infinity over infinity, which means you can either do L'Hopital's rule, do the derivative over the derivative, and then reevaluate as many times as you need to, as long as you're getting infinity over infinity or 0 over 0, or you can do dominant terms. So the dominant term in the numerator is 3n squared. There's only one term in the denominator, so I will look at 3n squared over n squared, and I know that that reduces to 3. So as n approaches infinity, this limit will actually equal 3. 3 is both finite and positive. So this series will do whatever this series did. They are of a size. So since this one converges, I know that the sum from n equals 1 to infinity of 1 over 3n squared minus 4n plus 5 converges not by the direct comparison test, but by the limit comparison test. The next video will show a few more examples.